Modern machine learning algorithms are incredibly sophisticated. We have the architecture to build brilliant artificial minds, but there is a massive bottleneck. These models are starving for data. To learn how to do anything effectively, they need to consume an enormous amount of real-world experience. Gathering that experience in the physical world is hazardous. If you want to teach a self-driving car how to navigate actual city streets, the trial and error process involves risking human lives and causing millions of dollars in property damage. And even for safe tasks, the process is staggeringly inefficient. If you need a computer vision model to recognize a specific brand of cereal, a human would have to manually photograph that single box from 10,000 different angles, under varying lights and backgrounds. That takes weeks of tedious manual labor. The solution to this data bottleneck is being built inside the video game industry. Developers are turning to Unity. Originally designed to build interactive 3D environments, this software acts as a high-fidelity matrix, an ideal environment to safely incubate artificial intelligence. A game engine gives researchers an infinite, risk-free sandbox. An AI can crash a car, drop a box, and fail 1,000,000 times, with absolutely zero real-world consequences. Think of this space as a virtual playpen. It starts as a completely blank 3D canvas, where developers have absolute control over the physics, the lighting, and even gravity itself. Look at this image of a simple, low-poly green car placed on a bare, tiled floor. We can use this basic environment and a process called simulation to teach an agent how to physically maneuver. Reinforcement learning is a continuous feedback loop built on 3 pillars: observations, actions, and rewards. At first, the car steers randomly and fails. Points are deducted from its counter, but eventually the car manages to drive straight. The system adds points, reinforcing that specific action. Because this is entirely software, developers can simply crank up the game engine's internal clock. The agent can run through 500,000 different driving scenarios in a single afternoon. Simulation bypasses the physical speed limits of reality. It compresses thousands of human lifetimes of trial and error into just a few hours of digital processing. Navigating space is only half the battle. A truly capable machine must also accurately identify the specific objects around it. To solve this, developers use a process called synthesis. Using tools like the Unity Perception Package, they build a completely automated, infinite digital photo shoot. This image shows the baseline setup. We import a 3D model of an object we want the AI to recognize, in this case, a cluster of green dice sitting on a gray surface. Next, we apply tools known as randomizers. These are scripts that rapidly manipulate the rules of our digital set. In a matter of milliseconds, these randomizers cycle the scene through thousands of variations. They constantly alter the camera angles, shift the lighting conditions, and change the floor colors. These images show the resulting data, perfectly labeled datasets of complex environments. On the right, the engine automatically partitions the regions, assigning specific colors to different objects. The AI learns exactly which pixels are a blue car, a green median, or the open road. By manufacturing perfect labeled visual data on demand, synthesis eliminates the data hunger bottleneck. The algorithms finally have the information they need to see clearly. Once the simulation and synthesis process is complete, the training stops. The AI's behavior model is locked in, and its neural pathways are finalized. That digital brain is not trapped inside the software. Using external machine learning frameworks like PyTorch, the fully trained model can be extracted and exported. This exported brain is then transplanted directly into physical hardware. It powers a physical pick-and-place robot, guides a self-driving car, or an AI-powered shopping cart. Game engines now function as high-fidelity laboratories for the robotics and automotive industries. They provide the sensory depth and physical accuracy required to prepare machines for the complexities of the real world. By simulating everything from engine temperatures to LiDAR sensors, these platforms remove the massive financial and logistical barriers to large-scale AI research. We can now design, test, and validate complex automation in software before a single piece of hardware is ever assembled.